lecture 35. Let's wind up current steering DACs today. I want to discuss a couple of important points. The first point being mismatch. So yesterday we saw that one way of increasing the output impedance of the current source that you have is cascoding. But so this is your whatever cascode. But the basic current source is this guy, and the current. So if what I equivalently do to set up a current is apply a constant voltage VGS between the gate and source of a MOSFET, and the current ID is nothing but K by 2 times VGS minus VT the whole square to to first order, right? I am now neglecting the effect of VDS and so on. The idea here is to basically see what happens when K and VT, as which we know are random variables. We'd like to find out how much the drain current varies when the K and the VT change with process. And from our discussion on DNL and INL in DACs, that the sigma I by I is the all important quantity which determines the DNL and INL. So what is delta ID? Delta ID is nothing but dou I by dou K times delta K plus dou ID by dou Vt times delta Vt. This equation, the second equation here, quantifies the change in the drain current due to a change in the K factor, which is mu1 C ox W by L, and a change in the threshold voltage of the transistor, which basically means that delta ID by ID is nothing but dou ID by dou K times delta K by ID plus dou ID by dou Vt times delta Vt by ID. And what is dou ID by dou K? Is 1/2 VGS minus VT the whole square, and this delta K, and ID is nothing but 1/2 K times VGS minus VT the whole square plus what is dou ID by dou Vt is minus K times VGS minus VT. What is minus K times VGS minus VT? Another minus K times VGS minus VT is nothing but minus GM, and this times delta VT divided by ID. And what is ID? 1/2 K VGS minus VT which means delta ID by ID is delta K by K, because this guy and this guy go away, and this guy goes away, and then you have minus 2 delta Vt divided by VGS minus Vt. So this equation here quantifies the change in the drain current, or the fractional change in the drain current for a change in K and a change in Vt. In practice, of course, delta K and delta Vt are not constant, but they are random variables, and as usual we assume that delta K and delta Vt are both Gaussian distributed with mean 0 and some standard deviation, in which case this delta ID by ID is now also this delta ID is also a statistical quantity. Delta ID square by ID square must be equal to sigma K square by K square plus 4 sigma Vt squared by VGS minus Vt. And when does this equation make sense? Both are random and what? And they are uncorrelated. And it's kind of reasonable to assume that this, without any information, the easiest thing to do is of course assume that they are uncorrelated and the math becomes simple. But it turns out that the guys actually made huge arrays of MOS transistors and measured the correlation between this sigma K and sigma Vt and found it's very small. So generally neglected. I mean, in principle, this K depends on mu n Cox. The threshold also depends on Cox, Vt. So it's actually quite reasonable to expect that the two will be correlated, right? Because they depend on something in common. But guys did measurements and then found the correlation. There is correlation, but it's very small, so you generally neglect it. As we were discussing this earlier on in this course, the sigma Vt square is of the form, or rather sigma Vt is of the form some AVT, some constant which depends on process, and divided by square root WL, where W and L are the dimensions of the transistor. And the square root WL has got, you can intuitively justify this equation by looking at what happens when the equivalent mismatch, when I take two identical transistors and put them together, right? So the equivalent mismatch, so if you think of, this is one transistor with size W by L, this is another transistor with, and this is some delta VT1, and this is delta VT2, okay, and this is a size W by L. Without these delta VTs, this is equivalent to a single transistor with a size 2W by L. And now when delta VT1 and delta VT2 are random variables, then I can, I should be able to express the effect of this delta VT1 and delta VT2 as an equivalent offset delta VT3 in a transistor of size 2W by L. And you can go and do the math. I mean, the change in the current there is nothing but delta VT1 times GM. These delta VTs cause a change in the drain current, and these two pictures will be identical when the change in the drain current in the lower transistor is exactly the same as the change in the drain current in the upper transistor. The change in the drain current in the upper transistor is delta VT1 times GM. The change plus delta VT2 times GM, and that must be equal to delta VT3 times 2GM. So, and now since delta VT1 and delta VT2 are identically distributed random quantities, the equation there basically means that sigma VT1 square plus sigma VT2 square must be equal to 4 sigma VT3 square. So, the equivalent offset has gone down by a factor of root 2. I mean, physically it means that you average out, many variables, and you average many times, and the randomness kind of reduces, right? Because you're doing better averaging, and every time you double the area, your standard deviation goes down by a factor of root 2. So that's an intuitive, way of explaining why the square root WL must come in the denominator. This AVT, as I said, is a process dependent quantity, and empirically people have found that AVT is about 3.4 millivolt micron plus half a millivolt micron for every 10 angstroms gate oxide. So, for example, in a 0.35 micron CMOS process, Tox is about 85 angstroms or so, and which means that AVT is 3.4 millivolt micron plus 4.25 millivolts micron, which is about 7. Similarly, in a 0.18 micron CMOS process, Tox is about 45 angstroms, AVT is 0.4 millivolt micron plus 2.25 millivolt micron, which is, so the AVT numbers will change for NMOS and PMOS, and it's a function also of the process. These are just ballpark numbers to get a rough estimate of these numbers, and in practice, whenever you are designing in a certain technology, the fab will give you, they will have made many transistors and measured these numbers, so they will give you these numbers, so there is no need to double guess and so on, but these are just good ballpark numbers to give you an estimate. Once AVT is known from the fab, the fab will also give you AK. Sigma K is of the form AK again by square root WL, and AK typically is of the order of a few percent micron. So anyway, does this explain why the oxide thickness, why this trend towards reduced AVT when the oxide thickness is made smaller? That should explain why the trend is there. Okay, so the first thing to do, I guess, when you want to design a DAC is calculate this quantity here. So this is known from the fab, this is also known from the fab, and then once this is known, depending on the architecture and desired resolution of the D to A converter, you know what sigma I by I you want. Once you know this equation, what does it fix? It fixes, and this are known, okay. So from this equation, and this is known from the architecture itself, so from this equation what you will be able to get is WL and VGS minus VT. There are many combinations of WL and VGS minus VT which will result in the same sigma ID by ID. So if you have a low voltage CMOS technology, right, if your supply voltage is limited, what can you comment on the VGS minus VT possible? You please note that you have to fit the entire current source, that which is the basic transistor, the cascode, the switch, as well as all these current sources go into a single load resistor. So the peak output voltage, the lowest voltage at the output is nothing but VDD minus. Yeah, so you have a whole bunch of these guys. The lowest voltage here is nothing but VDD minus 2 power n times I times R. So if VDD becomes small, so clearly this voltage must be such that none of these devices below get into the triode region. If I reduce VDD, what can you say about the VGS, the overdrives available for all the transistors below? Becomes small. So when you have a small VDD, it basically means that you have to have larger sizes because the VGS minus VT available is limited. So you can make a sane choice. So based on these considerations that you want none of these transistors to get into triode, even when the full scale, the DAC is exercised to full scale, that will basically give you a VGS minus VT to work with, which in turn will go and determine WL. As the resolution of the DAC required goes on increasing, what can you say about for a given supply voltage? If the resolution of the DAC goes on increasing, what happens to sigma ID by ID? It goes down. If that goes down, what do you think happens to, if you want to keep VGS minus VT the same, WL will become larger and larger. So once you get WL, the next thing to do is, this is fixed based on mismatch considerations. Then you add the cascode. Can you comment on how I should size the cascode before I do that? Is threshold voltage mismatch in the cascode an important thing or not? No. Why? Okay, in other words, what I'm asking, I guess, is this. So if I add a delta V here, which is equivalent to a threshold mismatch in the cascode device, so this is V bias 1. We saw how to generate V bias 1 yesterday. This is V bias 2, and we saw how to generate this also yesterday. If the gate source voltage, if the threshold mismatch and VGS changes by delta V, can you comment on the change in the current? What is delta I? So incrementally, what do you see? You have this transistor, and then this is the cascode device. The gate source voltage is pushed up by delta V. What is the resistance at the source? Is the RO of the transistor below, or a change in the threshold voltage, which is equivalent to adding a delta V, causes a change in the current. So what is this delta I? It is approximately delta V by RO. In fact, it really is delta V times GM by 1 plus GMRO, and if GMRO is very large compared to 1, which is definitely the case here, because if you want to make WL large, you go on increasing W, you go on increasing L, so the channel length modulation becomes smaller and smaller. Okay. In any case, this is approximately delta V by R naught. Can you compare the effect of offset here versus adding the same offset in this transistor? If this threshold varies by delta V, the current will vary by GM delta V, whereas if this threshold varies by delta V, the current will vary by 1 over RO times delta V. So clearly the threshold offset in the cascode device is GMRO times, the effect of the same offset in the cascode device is GMRO times smaller than the effect in the lower device. So bottom line is that the offset in the cascode device doesn't matter, which basically means that you can make the transistor smaller and smaller and smaller. So offset in this device does not matter. The next thing to do is to get into a switch. And then this goes to the load. So this is B bar and this is B, and how will the, so when you want to switch, basically what happens is that, okay, so one could be, okay, so clearly when one of the gates is much larger than the other, okay, all the current is steered through like this. On the other hand, if the opposite happens, all the current is steered through like this. Okay. Now let's see what happens. I mean, so the crucial thing is, so whenever there is a transition, whenever the waveform like this applied, where do you think all the difficulty lies? So anything that could go wrong will probably go wrong when there is a transition. Okay, so let's kind of spend a little time figuring out what happens during the transition so that we get some intuition about what you should do about these sizes. When you have a differential pair, it was going up like this and this chap was going down like this, what can we say about this waveform? So let's, for example, plot it on. So G1, G2, so this is VG1, VG, this is VG2, this is VG1. What is Vx? When Vg2 is much larger than Vg1, what happens? All the current goes into the transistor on the right. So what do you think is the potential at node Vx? It is Vg2 minus, this is nothing but the VGS, which is basically nothing but Vt plus square root of 2I by mu n Cox W by L. Now once all this action is over, what happens to, what is the potential? Let's do it on the other side of the graph. Hopefully we'll be able to interpolate. So once all the current is switched to the left transistor, which is what happens when Vg1 becomes much larger than Vg2, what do you see? You will see that potential again has to remain the same thing. Now let's try and do this at this point when both the transistors are on. So what do you think happens to that node? It is this voltage minus, from here we will have to subtract off, how much should I subtract off? Vt plus square root of 2i, okay, so I upon mu n Cox W by. So the output voltage will be something like, the waveform has to be symmetric around this point. Okay, so this is assuming that these are all slowly varying, right? So if you put a gentle ramp, that's the voltage. So we have basically neglected all capacitive currents. Okay. In practice, of course, there is always parasitic capacitance at this node. And why is this parasitic coming? The total capacitance at this point is the gate source capacitance of these two transistors, these two switching transistors, plus drain capacitance of, so this is the parasitic output capacitance of the current source plus, this capacitance plus that guy there. Now let's assume Cp is very small, so that this waveform doesn't, is still the, to analyze what happens when there is C, to get a feel for what happens when there is Cp, this is a reasonable thing to assume. If there is something like this, what do you think will happen to the current? What is the extra current that is being injected into this node? Is the switch waveform, the control waveforms are doing this, then what happens is that the source coupled node is basically doing that, which basically means that the current, the displacement current flowing through the capacitor is nothing but Cp dV dt, correct? So what is that current? How does it look like? It will go, it is 0 here, then what happens? It goes negative, it goes to 0 here, it goes back to 0 here. So let's see, so this is the, this is a very first order analysis of what happens. Now when you are in this region, where do you think most of this displacement current flows? It goes, does it flow towards the left or the right? It flows towards the right. During this half, it flows towards the left. So the exact fraction and all, it hardly makes any sense to compute because we are doing such an approximate analysis. So ideally what we were expecting, we would expect the current to just switch from I to, from the left leg to the right leg without any, without you being able to notice anything. But now what do you see? You see that you not only have the DC current I, the tail current I, but you also have a displacement current through the parasitic capacitance at that node. The current waveform through each of these resistors, load resistors, is what? It will be the DC current plus the displacement current. So what do you think, if I plot this waveform, what do you think will happen? Ideally you were expecting the waveform, the current on the transistor towards the right to be doing this. So during, when Vg2 was high, you were expecting this, all the current I, so I2. So when Vg2 is high, all the current should flow through transistor 2. Then what, now what happens? And just the static part of the current should basically become I by 2 around here, and then do this. This is what you would expect, okay? So and clearly as the switching waveform becomes faster and faster, this approaches a step. Now what happens, in addition to this, there's a displacement current. So what do you think will happen? we kind of make the vague approximation that during this part of the cycle, before the cross point occurs, the displacement current is flowing in this direction. So the total current is basically the displacement current plus the static part of the current. So which must so you need to add this up. So what happens is basically in the left transistor it can be approximated to be something like so now if the edge becomes sharper and sharper and sharper, what do you think will happen? If the edge becomes, if the transition becomes shorter and shorter, what will happen to this guy? This will become thinner, skinnier and taller. So what does this become? So this will drop by a large amount, okay, and then come back. So in other words, this basically instead of having a nice clean, step-like transition, there will be a glitch at that point. Basically, parasitic capacitance at this source coupled node basically causes a glitch, and it turns out that this is what causes. This causes, if you go into a careful analysis of waveform and do the math, it turns out that this causes distortion. Can you give me an intuitive feel to why this results in distortion? Okay, one simple way of understanding it is that, I mean, you can go back, you can think about it in the same way as we discussed when we discussed rise and fall time asymmetry in DACs. Okay, so if this was, let's just consider this to be a 1-bit DAC. So there are only two levels, either 1 or -1. Whether you put in a 1010 sequence or 1111 0000 sequence, the mean must be the same. Correct? This is a linear affair. And if this is linear, when I put many of them together in parallel in a thermometer DAC, thermometer fashion, that must also be linear. So it will suffice to analyze just this. So clearly, if the input sequence is 10101010, you see that you are getting hit every time. Every time there is a transition, there is you are making some error. But if you have only one transition in a whole string of bits, then you find that you are making only one transition over so many bits, right? So the error will be amortized across several number of ones. So the mean in both the cases is definitely not the same. Okay, that's enough to prove that this causes nonlinearity. There are several clever solutions proposed to kind of clean this up. One solution is deliberately cause a glitch every time by some clever arranging logic in such a way so as to cause that node to glitch every time, regardless of whether there is a transition or not. So that basically greatly reduces distortion. But the cleanest, safest way of doing it without too much effort is to make sure what? Of course, you got to. So the first thing is, of course, you want to minimize CP as much as possible. So what does that mean? The switch should be as small as possible. And of course, and the parasitic capacitance, I mean, so basically you want to minimize CP, so the switch must be as small as possible. And the drain capacitance at the capacitance at the top terminal of I must be as small as possible. And thanks to the cascode, that is possible because, see, for matching reasons, you need the lower transistor to be huge, correct? If you didn't have a cascode, you have a double whammy because, first of all, the output impedance, I mean, is smaller. The DC output impedance is smaller. More importantly, without the cascode device, the transistor, the W by L of the transistor is the same of both the devices, the cascode as well as the bottom transistor. But the W into L for the bottom transistor is much larger because you want to reduce mismatch. So which basically means the W is large and the L is large. If the W is large, what does it mean for the capacitance? It's large. So the cascode is doing two things. One, it is enhancing the DC output impedance. Two, it is also enhancing the AC output impedance. The AC output impedance earlier was simply the big capacitance of the lower transistor's drain. Now because of the cascode, which can be made much smaller than the lower transistor, because the mismatch in the cascode is not an issue, the tail, the capacitance at the drain of the cascode is also much smaller than it would be if the cascode wasn't there. That also helps in greatly in reducing distortion. Okay, so so to minimize distortion, minimize switch size, reduce parasitic capacitance of the current source as much as possible, and the third one and the last one of course is to this takes care of minimizing glitch current by, we know that glitch current is Cp dV dt, dVx by dt. So there are three ways of minimizing glitch current. One is reduce Cp, one is reduce dVx by dt, okay, and the third is to do both. This takes care of doing your best as a designer to reduce Cp by intelligent choice of device size. The third one is to minimize dVx by dt. In other words, while switching, what you want to do is to minimize voltage variation at this node. Two distinctly okay, there's one distinctly bad way of doing this. What do you think if we did this? Somehow things were bad in the design and the complement came much later. So this is VG1, this is VG2. So during this period, what happens? If both these voltages become low, then both those transistors are tending to go off. So what do you think will happen to the tail current node here? Assume this goes all the way from 0 to VDD, right? So if both these transistors are connected, the gates are connected to 0, both these transistors are off at the same time. And so what happens to this node? There is a parasitic capacitance Cp here, and there is a current flowing. So what will happen to that node potential? All the current which was supposed to get sucked out through the transistor sources has nowhere to go. So it will suck charge out of Cp. Okay, so what will happen to this node potential? During this period, okay, the voltage is something here, it was kind of doing something like this, then it will glitch big time, and then do this and then come back. The one thing that you absolutely need to do is make sure M1 and M2 are never off simultaneously. What do you think happens to the tail node when the opposite thing happens? So this is VG1, this is VG2. What do you think will happen to the waveform at X if this happens? So if these both become simultaneously on, please note that when there is the transition exactly at the middle, there is a glitch, correct, because Vx is doing this. So if both of them are on for some time, what do you think will happen to this glitch? It will reduce because this thing will tend to move up. So a standard way of reducing voltage variations at Vx is to keep M1 and M2 on for a small time. In other words, this point, which is called the cross point, must be manipulated by changing the timing of the two signals which come there by making sure that M1 and M2 both conduct for a short interval.